Welcome to Unit 1, Lesson 1, Part 1. I'm Mr. Polarski and I'm your math teacher this year. Today we're going to be working out of Lesson 1.3 from the Pearson Copyright 2009 edition. Today we're going to be talking about exploring real numbers. Our objectives today are, I will be able to classify numbers and I will be able to compare and order real numbers. Here we're going to be talking about different ways to classify numbers. First, we have the natural numbers. You can see those numbers listed here: 1, 2, 3, and then dot, dot, dot. That dot means that pattern continues on. 1, 2, 3, 4. Notice it's none of the numbers in between. It's the natural numbers over here on the number line. 1, 2, 3. Really, we should bold this to indicate that that goes on forever, meaning all 4, 5, 6, 7, etc. Now notice the difference between the natural numbers and the whole numbers here. The whole numbers have the number 0 in it. So the whole numbers are all of the natural numbers plus 0. So we can see that here, and really we should bold this arrow indicating that that goes on forever. Now what the integers are the whole numbers and their opposites, meaning 1 and -1, 2 and -2, 3 and -3, and so on, again indicated by these 3 dots. And in both of these cases, these arrows should be bolded to indicate that that goes on forever on the number line. Next we have the rational numbers, and here's a little typo. It says the rational numbers is. Rational numbers are any numbers that can be expressed in the form a over b, or in other words, as a fraction. Where a and b are integers and b is not allowed to be equal to 0. Now let's take this and see if we can identify some numbers in our following examples. Here we're going to be classifying numbers in example 1t. The directions tell us to name the set of numbers to which each number belongs. Now in example 1t, first we have the number -13. Now if we think about back to the last slide, okay, we had the natural numbers, the whole numbers, the integers, and the rational numbers. Whole numbers didn't include any negatives, and neither did the natural numbers, so we know it's not going to be natural or whole. Now the integers were the whole numbers and their opposites. So -13 is the opposite of 13, so we know that this is an integer. And since it's an integer, it's also going to be a rational number, because we can express it as a fraction, -13 over 1. Now part B here is positive 3.28. And positive 3.28, that's just a rational number, because natural numbers do not have fractional parts, whole numbers do not have fractional parts, and integers do not have fractional parts. Rational numbers are any number that can be expressed as a fraction a over b. Well, here we'll be able to take this decimal. You might be thinking, well, there's no fraction there. Well, really there is. A decimal can be expressed as a fraction. So this thing's going to be rational. And that's because 3.28 can be written as 3 and 28 over 100. Now the reason it's 100 is because 0.28 is 28 hundredths. Then we change this mixed number to an improper fraction by going 100 times 3, which gives us 300, and 300 plus 28 is 328. And the denominator is 100. Now, that fraction does reduce by a factor of 4. If we divide both the numerator and the denominator by 4, that leaves us with 82 over 25. So there's our proof that 3.28 is, in fact, a rational number. Now, part C, we should clearly be able to see that this is a rational number, and that it's not natural, and it's not a whole number, and it's not an integer. It's clearly a fraction, 13 over 5, where a is 13 and b is 25. We're continuing our work with classifying numbers, and in example 2, we're going to take a look at some real-world examples. The question is, which set of number is most reasonable for each situation? Part A, outdoor temperatures. When we talk about outdoor temperatures, probably the most realistic place you see that is on the news, or on the Weather Channel, or on your computer, maybe the Weather Channel app. You never know. But anyway, outdoor temperatures are always expressed as whole numbers. But if you live in a colder climate area, then you may have to be dealing with negative temperatures, temperatures below zero. So not only would you be talking about whole numbers, you'd be talking about integers. Now you may want to argue that you might be dealing with temperatures in half degrees or tenths of a degrees, which would then make that a rational number. But typically those degrees aren't talked about unless you're talking about very scientific testing situations where you'd be finding the melting point of a particular metal or something like that. So part B, the number of beans in a bag. Now the number of beans in the bag, I'm going to consider the best answer here to be the natural numbers. Now some people might argue that if there are no beans in the bag or 0 beans in the bag, then we could argue that this could be the set of whole numbers. But if you don't have any beans in the bag, why are you talking about the number of beans in the bag? Here we're continuing to classify numbers, and we're going to add to that 2 more classifications. First, we're going to talk about irrational numbers. And irrational numbers cannot be expressed in the form A over B. Look what I did there. I made that a fill in the blank a fraction line, but they cannot be expressed as a fraction in the form A over B. Here we have our rational numbers on the left of this blue line. That's one set of the real numbers, and then the other set of real numbers is the irrational numbers. The square root of 24, if you did that on a calculator, it'd give you a decimal number that did not repeat or did not terminate. It's the same with the square root of 10. This thing E, that's the natural log. Pi, 3.14 in many, many decimal places. Those are irrational numbers. Here's some other irrational numbers. Here I have pi again, the square root of 12. This here, it has a pattern, but it's not a pattern that's repeating. And it says here that the addition of the irrational numbers creates the 2 sets of the real number system. And I forgot the word real in there, so you're going to want to write that in there. Real number system. Okay, so we can see the real numbers are made up of rational numbers and irrational numbers. The question here is, what is a counterexample? And there are 2 things that we really need to know about a counterexample. First off, we know what it is. We need to know what it is. Any example that proves a statement false is a counterexample. That'd be like your definition. The second thing, you only need to find one counterexample to prove a statement false. So if you have a statement of some mathematical reasoning or some philosophical reasoning, you only need to find one counterexample to prove that given statement false. We're going to see how to use or find a counterexample to prove statements false in the next examples. Here in example 3T, we're going to be using counterexamples. We're told to determine whether the statement is true or false. If it is false, give a counterexample. As we discussed in the previous slide, we only need to find one counterexample to prove a statement false. The statement we're given is that all negative numbers are integers. We assume that to be true until we can find a counterexample. Now, all negative numbers are integer is a false statement. And the example, and you could have many different examples, it doesn't have to be the same as mine, but the example that I chose to use is negative 3/5. Negative 3/5 is a rational number because 3 over 5 is expressed in the form a over b, or as a fraction. It's a rational number and it's negative. Therefore, negative 3/5 is my counterexample to the statement, all negative numbers are integers, because I found a negative number that is not an integer. Symbols to compare numbers. This is taken straight from Pearson, copyright 2009, Algebra 1. It's the book with the green cover, and this is from page 19. An inequality is a mathematical sentence that compares the value of two expressions using an inequality symbol, such as less than or greater than. When you compare two real numbers, only one of these can be true at a time. A is less than B, or A is equal to B, or A is greater than B. We have three other symbols that we use in math. They are less than or equal to, not equal to, or greater than or equal to. This number line shows how the values of numbers increase as you go to the right on a number line. Starting at the left, going to the right, the numbers get bigger. -1 to +1, the numbers get bigger. Since -8 is to the right of -1/2, -1/8 is greater than -1/2, and -1/2 is less than -1/8. Also, we could say that -1 is less than -1/8, or we could say -1/8 is less than 0. It works. The symbol you use depends on the order of the numbers. Here we're still comparing numbers, but instead of using greater than or less than, we're actually going to be putting the fractions in order in this example 4t, where it's called ordering fractions. To compare fractions, you may find it helpful to write the fractions as decimals and then compare the decimals. Now that's a basic math skill that you should know how to do, is convert a fraction into a decimal. Many times students don't know how to do this. We have to divide the top by the bottom, or have to divide the numerator by the denominator. That quote's from Prentice Hall, Algebra 1, copyright 2009, page 19. So here we're going to write -3/4, -7/12, and -5/8 in order from least to great. So we're going to put them in order from small to large. So to do that, we need to change -3/4 into a fraction, or into a decimal, that fraction into a decimal, where we're going to take 4 and divide it into 3. That's exactly what a fraction means. But you should know you can't divide 4 into 3, so what we do is we add a decimal and a 0. Actually, we're going to add 2 zeros here. And this may be a fraction you know. It's 0.75 or 3/4, but 4 goes into 30 7 times. 7 times 4 is 28. Subtract, that leaves 2 left over. I bring down the 0, and 4 goes into 20 5 times. 5 times 4 is 20. We get nothing left over. So the first number here is -0.75. The second number we'd convert in the same way. I'm not going to take the time to do that, but if we were to convert 7/12 goes into 7. Remember, add a decimal and a couple zeros. You're going to find out that when you divide this out, it becomes 583.583, and that 3 ends up repeating. Remember, that's a negative. And finally, we have -5/8. And again, to set that up, we'd go 8 divides into 5. Remember, it doesn't divide in, so it'd be 5.0. In this case, we'll go a few zeros. And when that comes out, that'd be a -6.25. And that does terminate. So putting these numbers in order from smallest to biggest, the smallest number here is -0.75. The next smallest number is -0.625. And finally, the biggest number is -0.583. So putting these fractions in order, number 1 from smallest would be -3/4. The second number would be -5/8. And the third number would be the -7/12. So we divided those out into decimals. You could use a calculator to do that, or do it by hand. An absolute discussion. Take 1. Action. Still comparing numbers, we have to have an absolute discussion here. Two numbers that are the same distance from 0 on a number line, but in opposite directions are opposites. Make sure you fill that in on your notes. We can see here, it says -3 and 3 are the same distance from 0. You can see that on the number line. They're both 1, 2, 3, 1, 2, 3 units away from 0. So negative 3 and 3 are called opposites. The absolute value of a number is its distance from 0 on a number line. How many units away it is. Here, it's 3 units away. Here, it's 3 units away. Both negative 3 and 3 are 3 units from 0. Both have an absolute value of 3. You write the absolute value of 3 as these two vertical bars. That's the symbol, these two vertical bars. That's taken from Prentice Hall, copyright 2009, page 19. One thing to note about the absolute value, it's always positive. The absolute value of a number is always positive. Example 5T, finding the absolute value. Take 2. Action. In example 5T, finding the absolute value is the goal. We're told to find each absolute value. For part A, we have negative 2.5. In relation to the definition we just discussed, we have negative 2.5. It's a number's distance from 0. Well, negative 2.5 is over here, and it's 2.5 steps away from 0. So the absolute value of negative 2.5 is 2.5. Notice the absolute value is always positive. Here, we have the absolute value of 7. Again, in relation to a number line and its distance from 0, the number 7 is 7 units away from 0. So the absolute value of 7 is 7. The absolute value of a number is always positive. Sorry, I just banged my microphone there. But the absolute value of 7 is always 7. The absolute value of a number is always positive.